Differentiation, page 6. So we're going to work with more word problems here. A lot of these word problems, even though they're considered differentiation and calculus problems, you might never have to do any calculus on these problems. You might think, oh my gosh, this is just like second calc max and second calc min problems we did in the past. So don't be afraid, okay? So there's something on a curve called a stationary point. What is a stationary point? A stationary point is a place on this hill or in this valley where you can perfectly balance a ball and it will not roll away, okay? This is pretty obvious. You can put a ball here, it's not going to roll away, right? This is a little bit less obvious. At the very top of the hill, if you put a ball at the very top of the hill and it's perfectly balanced, it will not roll away, right? Because right at the top of the hill is flat, right? So that's called a stationary point. The slope of the hill at the top is flat, and the slope at the bottom of the hill is flat. And you might say, no, it's not, it's curved. Well, think about it. As you're going up the hill, the slope is positive, right? It's going up, it's positive. When you get to the top of the hill, suddenly it starts being negative. The slope starts being negative, right? The slope cannot transition from positive to negative without, for one split second, being zero, right? So where does that zero slope take place? Right at the top, okay? So if we find the place where the derivative is zero, then we either have found a maximum or a minimum. One of the two, a local maximum or a local minimum. Remember when we heard that before? Local maximum, local minimum. So local maximum and local minimum points are stationary points. Okay? All right. Now that we know that, let's do problem 1. Jules throws a stone into the air. The height of the stone can be modeled by this equation. Okay? Where t is time in seconds that has passed since the stone was thrown, and f of t is the height of the stone in meters. So the y or the output of the function is the height, and the input is the time. T is time usually. Okay? So first it says find the derivative of f dash of t. So we just use the power rule. So what's the derivative of 1? It's 0. What's the derivative of 7.25 times t, or x? 7.25. And what is the derivative of 1.875 t squared? It would be 1.875. You just write the number again. You bring down the 2, and then you reduce the exponent 2 to 1. So our final answer is 7.25 times, let's do 1.875 times 2 in the calculator to simplify it. 1.875 times 2, negative 3.75 to the t, or t to the first. And we don't need to write to the first, right? So there is my derivative function. Now it says to find the stationary point and then show that this is a maximum point. Okay, so let's put both of these functions in the calculator, shall we? So I'm going to put the original function, which is the height function f, in y1, and then I'm going to put the derivative function in y2. So 1 plus 7.25 x minus 1.875 x squared. That's my height function. And then I'm going to put the derivative function, which is 7.25 minus 3.75, in y2. Okay, and then I'm going to look at the table. Okay, remember I changed it last class to jump by 10s. I'm going to jump by 1s again. Okay, and so when I look at the table, what I'm looking for when I'm finding the stationary point is I'm looking for when the derivative is 0, right? When the derivative is 0, the slope is 0, and that would be my stationary point. You might say, well, how am I supposed to find it? Well, remember, the 0 occurs when you transition from positive to negative. Here's positive, here's negative. Obviously, it's going to happen between 1 and 2, right? So let's use our technique of changing the step side to like 0.1 so that maybe we can find it. And let's see. It looks like it's happening between 1.9 and 2. So now we're going to change our step size to 0.001. See if we can find it. Oh, actually, I wanted to change the size to 0.01, not 00. Did I say 001? That's way too small. Okay. Now we have, it's somewhere between 1.93 and 1.94. Okay, and this is already close enough. We don't need the t value more than 3 sig figs. This is 3 sig figs. So you just look at 1.93 and 1.94. Which one is closer, 1.93 or 1.94? Looks like 1.93 is closer. So the answer is going to be t equals 1.93. That's where our stationary point is. If we want to know what the y value is at that point, I'm not sure if they want to know, it would be 8.0083. So if I was to say the stationary point, I could give it as 1.93 comma 8.0083 or 8.01. Okay, show that this is a maximum point. Okay, we can show that this is a maximum point by looking at the red numbers, right? Remember that a maximum point occurs when the values to the left are positive because the slope is going up, and the values to the right are negative because the slope is going down. Let's look at the red numbers. So they're positive, 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 and then they transition to negative, 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 negative. So that's how we can show that the derivative can prove that this is a maximum point, because the numbers to the left are positive numbers, and the numbers to the right are negative numbers. So I could say, now this part of it, I would say, is for extension, okay? So the derivative is positive when t is less than 1.93. And the derivative is negative when t is greater than 1.93. So that's how we can demonstrate that this is a maximum point, okay? All right, number 3. The path of a shot put can be modeled by this function, where t is the time in seconds and f of t is the height of the shot put in meters. Have you noticed the patterns? The x coordinate is usually time, and the y coordinate is usually like a position. In this case, it's a height. Find the maximum height of the shot put and the time when this occurred. Now notice carefully that this problem did not ask you to find the derivative. Guess what? We're not going to find the derivative. Okay? In our class, we have perfectly good ways of finding maximum height without finding the derivative. So if they didn't ask us to take the derivative, we're not going to take the derivative. We're just going to type the function into the calculator and do second calc max. So that's what we're going to do. See? Calculus problems are not necessarily hard problems. X squared. Okay, and then I'm going to graph it. And now the challenge of some of these real life problems is that they don't fit in the standard negative 10 to 10, negative 10 to 10 graph. This one, we're lucky it did. The maximum point's right there, right? How do we find the maximum point? Second calc, maximum. And then we do the left bound. It could be to the left of the peak. And then we move the cursor using, move the cursor using the right arrow so that we're to the right of the peak. And then we hit enter. And then we do a guess. We just hit enter. And the maximum is 6.00006, y equals 4. Let's just call that 6, 4. Okay, so what's 6? 6 is the time that it happened, and 4 is the height. Okay, find the maximum height. So they want to know 4 and the time. Oh, they want to know both. So it's a good thing we wrote both down. So the time is 6, the height is 4. All right, next one. Number 4. Ooh, this is a nice business one for you business guys. Okay, once again, the profit P that Yorona makes each day is dependent on the number of brownies N that she bakes. Remember when we did the problem yesterday about bake sale 2? Her daily profit can be modeled by the function P equals blah, blah, blah. Find the maximum profit that Yorona makes in a day and the number of brownies she needs to sell to make this profit. So in this case, the X coordinate is N, which is number of brownies, and P is the profit. So all we need to do is put this in the calculator to do second calc max because we want the maximum profit, and we'll find both the X coordinate, which is brownies, and the Y coordinate, which is maximum profit. That they want to know both, right? So let's type this in. Negative 0.056 X squared plus 5.6x minus 20. And then we're going to graph. Sometimes we're not even going to see the peak, right? So if you can't see the peak, my advice is on these real life problems, change the window to 0 to 100 and then 0 to 100. Y min 0, 1. Usually real life problems have the advantage that negative numbers are meaningless. So there's no use plotting the negative part of the X interval and the Y interval. And the other thing that happens in real life problems is usually the numbers are bigger, like 100. So let's see if that's big enough. Almost. It's almost big enough. It's a little bit cut off. How can we adjust the vertical? We could just do Y max 200 instead of 100. Or we could do zoom fit, right? Because zoom fit adjusts the vertical. This is going to be good. Okay, and so now we're just going to do second calc max, right? Second calc max, number 4. Left bound, we're going to move the cursor slightly to the left of the peak, enter. We move the cursor slightly to the right of the peak, enter. And then guess, enter. The max is 50, 120. 50, 120. 150 is number of brownies, 120 is the profit. And they want to know both. They want to know the number of brownies and the profit. Okay? All right. That wasn't too bad, right? That was a business one, typical of a business one. John is a keen cyclist and is planning a route in the Alps. The profile of the route he would like to take can be modeled by the function blah, blah, blah. A profile of a route just means like the side view of a route, okay? Where y is the height of the point, it's like hundreds of meters, on the route that is a horizontal distance, which is tens of kilometers from his starting point. Okay, plot the graph and find the maximum height. Okay, so one more time, all we're doing is we're going to type this in the calculator. It's going to take a little bit longer because it is a long function that has to the fourth right arrow plus 0.89 x cubed minus 2.87 x squared plus 3x. And they even tell us that the domain is between 0 and 6. Now that makes it a lot easier to graph if we know that the domain is between 0 and 6. I'm going to make the y a little smaller. I'll just put like 40. I don't know what it's going to be, but 40 is too big, obviously. Okay. I'd say 10 is enough, wouldn't you say? We'll go from 0 to 10. See how that works. We could have done zoom fit too, right? Okay, so this is the side view of a mountain. This is the path that Jean is going to cycle. Okay, so we're just going to find the maximum height that John will climb to. It's obviously not this one, it's this one, right? Second calc, maximum. We've been doing maximums, but we could do minimum too, right? Especially on this one. And then we'll do right bound. We'll move the cursor to the right of the peak. Then we hit enter, and then we hit enter again for guess. And the answer is not a nice number, but that's okay. We'll put 5.15, comma, 3.92. What's wrong with my pencil? Why is it freaking out? Maybe it's running out of battery. 3.92, 5.15. Okay. So the x coordinate is horizontal distance by 10 kilometers. And the y coordinate is 100 meters times that. So actually it's 1.5 kilometers and 392 meters. Okay? So let's see, plot the graph and find the maximum height that John will climb. So the maximum height would be the second number, the y, and so it would be 392 meters. I think that's all they want to know. Yep. Okay. If you want to graph this on paper, of course you would do second table, and you would, of course you would, let's do second table set 0, 1, so that we'll have reasonable numbers. And then you could grab some of the numbers from here between 0 and 6, right? And you could graph those. Okay, that's it for this page.